We'll first navigate to all topics, where we have a topic created for transformers. The first chapter, why sequential models hit a wall. We'll click on that. The first section talks about sequence challenge. Before we can build machines that understand language, we have to understand what language actually is. Unlike a single image or a flat table of house prices, a sentence is not a static object, it's a sequence, an ordered list of items where the meaning of an individual word is deeply tied to the words that came before and after it. So the relevance of word actually depends on the tokens that are coming before and after. So if we change the order, we'll definitely get a different meaning of sentence. For example, the dog chased the cat chased the dog. They are two different meaning sentences. Standard traditional neural networks treat inputs as independent of one another. So to handle language, we needed a class of models designed specifically to process data step by step. So previous generation of models, they treated all the inputs as independent of one another, and as we saw for language, we cannot do that. Why do standard feed-forward neural networks struggle with natural language processing? It spoke about it. It assumes inputs as independent of one another, and it ignores the sequential order which is required for getting the output in natural language. So recurrent neural networks were designed by researchers because of this problem, and the core intuition behind RNN was simple. It processes sequence one step at a time, keeping a running memory of what it has seen so far. Think of it like reading a book. You don't forget the first part of the sentence when you're reading the last word. There is an internal mental state that updates with each word. So it's a neural network which connections between nodes from a directed cycle along with a temporal sequence. This allows the network to maintain an internal hidden state. We talked about it. This is a state or a memory which is keeping the meaning of the sentence till that point. You can think of it like that, and it is denoted as HT. Math. At every step t, the RNN takes the current input word vector xt. So all the inputs are first converted into vectors, and the previous hidden state ht minus 1. So in RNN, the hidden state depends on the hidden state of the previous token. I have got a diagram to explain this as well. Think of it like think of this example: the dog chased the cat. For the token we have a hidden state which depends on h0, which is null, but for the token dog, it actually depends on ht minus 1, which is and similarly for chased, it depends on the hidden state of dog. So the last word cat depends on the previous word which depends on chased, which depends on dog, and dog depends on So eventually cat depends on all the previous words, but the relevance of each word gets diminished because we change the weights during training. And we multiply it with less than 1 to ensure that it doesn't come as frequently, and that is what the vanishing gradient problem is. Let me ask this to the model as well. Give an example of the problem. Okay, so sentence it talks about is: I grew up in France. I speak fluent French. If an RNN suffers from, it might result into fluent English. Why this happens is the RNN needs to remember the word France from the beginning of sentence to predict French at the end. But with long gap between the relevant context, which is France, the most relevant token, And prediction point, the gradient signal vanishes during back propagation. Let me minimize that. This is the formula for RNNs. What is the mathematical driver of vanishing gradient problem in RNNs? Mathematical driver is addition of bias. No, it's the repeated matrix multiplication of weights. And it's because of back propagation again, because through time it requires multiplying the recurrent weight matrix at every step. The hardware wall, because of the sequential nature, which is the step-by-step processing of RNNs, so GPUs are not designed to do complex deep calculations one after another. Instead, they are designed to do millions of simple calculations at the exact same time. This is called parallel processing. And if we want to train a model on billions of words, we must be able to feed those words into a GPU and process them in parallel. Like currently, all the models that are using transformers architecture, they do the same. Sequential dependency is a computational constraint where a step T cannot begin execution until step T-1 is completely finished, which we saw in RNN. In sequential, we cannot utilize GPU as high as in parallel execution. And the training time also linearly increases with sequence length, while it is highly independent of sequence length in parallel execution. And that is very critical, because if we want to train the entire internet's data, we must not couple the length of the data size with training time. Fix the vanishing gradient problem. LSTMs and GRUs were created by researchers. Means long short-term memory and gated recurrent units, GRUs. These models introduce something called gates. These are gates for input, forget, and output. The only problem with LSTM were it required even more matrix multiplication per step than standard RNN. So the problem with taking advantage of GPUs, that was even higher for LSTMs, while it did reduce the vanishing gradient problem. The quick check-in is also asking us the same question, which is why it failed to unlock the training of massive modern LLMs, because failing to utilize the GPU parallelization. To break this wall, we needed an entirely new paradigm, transformers, one that could process whole sentences at once completely in parallel without losing a track of word order.